Hello, I'm looking again at this 4S sodium ion battery, and one of the first things I'm going to do is take off these BMSs because they never really worked. This is an NMC BMS, but the trouble is it cuts off at the high end at about 4.3 volts. That's too high for sodium ion, so it doesn't protect them from overcharge. And this LFP BMS cuts off at the low end. This was meant to protect against undercharge or over discharge. I think at about 2.5 volts. Well, sodium ion can go down to 2, can even go down to 1.5. Well, it can even go down to 0 volts, we're told. Now, I've been charging this recently and it's quite well charged, so I don't want to short anything out. So I'm going to lift these two plugs out like so. That means all these BMS measurement wires are now effectively disconnected, so I'll desolder all of that. Let's have a gratuitous desoldering shot. Do I want to take that one off? Yes, I do. And let's take these off. Okay, that's half of it off. And this one I can't desolder because I've made the mistake of soldering it right up on the flat of the cell, and of course it's drawing all the heat out, so I'll just cut that one. So what am I planning to do once these BMSs are off? Well, I'm not going to have a BMS. What I want to do with this, a bit like those LTO cells, I want to try and use this with just a balancer and no BMS. Now, I do have a 4S balancer on here, this 100 balance unit, but I'm going to complicate things a little bit by taking this up to 8S. I want this to be an 8-cell sodium ion battery. So it's going to be 32 volts at the top. That's if you take the cells to 4 volts each. And 16 volts at the bottom if you discharge to 2 volts. So here are the other 4 cells, and I've got more of these holders, so I'm going to build it up to twice the height. These are sodium ion. I don't know whether that code gives that away, but possibly the fact that they're nominal 3.0 volts tells you they're sodium ion, because LFP would be 3.2 or 3.3, NMC would be 3.7, and also the capacity 30 watt hours relative to the size perhaps gives it away as well. So I've got to build that up. Now that of course will mean taking off the 4S balancer and going for an 8S unit. Here are some balancers. This is a 3S. There are 3 MOSFET chips on here. They're dual MOSFETs. This 4th chip, you can see with the diode running along the side of it that it's a MOSFET driver. So this 4S balancer has 4 MOSFETs and a MOSFET driver and a little oscillator chip. It's a microcontroller, I'm pretty certain, but I think its role is little more than an oscillator. And this is the 8S balancer. Now what's interesting about this is it has 4 MOSFETs here. That's the MOSFET driver. I should get a pointer really, shouldn't I? I've got one here. But here it has 5 MOSFETs and another MOSFET driver, and there's the little oscillator chip there. So why does it have 4 MOSFETs and 5 MOSFETs? Because that adds up to 9 when it's an 8S balancer. Well, this is actually 2 active balancers, capacitor-based active balancers, and they're overlapped. So if you take, say, this is 3 cells here, the gaps, and this is another 3 cells, they overlap them like that, so that the voltage of this cell can be passed down this chain, but also up this chain. So the overlapping is done on here to overlap the 4 and the 5. But why don't they just simply have 8 MOSFETs, all driven by this MOSFET driver? Well, that's an interesting question. And it has to do with the way these MOSFETs are arranged. So like I said, these are dual MOSFETs. So I'll draw the circuit for a 3S balancer. It is simply 6 MOSFETs. And they're stacked like this. This is the 0 volt line here, and they're stacked all the way up to the positive of the top cell. Now the cells are sitting here. So I'll draw the cells. I'll complete that off camera. So the cells are like this. This is cell 1, cell 2, cell 3 for the 3S unit, which means that these points here are all at different potentials, but the gates are all common and driven by one MOSFET driver chip. So these MOSFET gates are all driven by the same output. This will be either the high or the low output. Let's call it the high output. So the high output is just sent to the gates of these three MOSFETs, but the sources are all at different potentials because of the three cells. So you get this very curious situation where the voltages that they're using to switch the MOSFETs are different for each MOSFET. So this bottom one here, actually I haven't drawn it properly, but this one will be switched off at 0 volts because the low output of this chip, well, I could draw that in actually. The low output of that chip comes down and goes to this bottom MOSFET. So this will be switched on with a high potential. This potential up here actually is what's driving the MOSFET driver to turn this on, and 0 volts to turn it off. But this MOSFET up here is turned off with a negative voltage because it'll have 0 volts put on it, but that's 0 volts down here relative to the source, which is this could be, say, 4 volts. Let's call these 4 volts each if they're fully charged sodium ion. And this MOSFET up here will actually have minus 8 volts on it for its switch off, and about plus 4 volts on it for its switch on. So plus 4 to minus 8. This one would be plus 8 to minus 4, and this one will be plus 12 volts. This one down here, switched on with plus 12 volts and switched off with 0 volts. And they're using the fact that MOSFET gates have a fairly wide voltage range within which they'll function, typically up to about 20 volts. Although I suspect that with this 5 array of dual MOSFETs here, it's going to be very close to that, or even perhaps above. And also, of course, you can turn them off with negative voltages. The MOSFET gates are quite happy to have a voltage down to, say, minus 20 volts. And so this array of 5 dual MOSFETs actually gives you 10 of these MOSFETs all stacked on top of each other. Now, if this has 4.2 volts on it, which is perfectly possible because it's NCM and LFP, it says it somewhere down there, I think. Yeah, NCM LFP. You will have more than 20 volts on the gate of the, what is it, the bottom MOSFET, because to switch that on, it's going to have the full, this MOSFET driver is powered from this top cell. So you've got the full potential of, well, 5 in this case, lots of 4.2 volts as the on voltage. That's going to be quite high. Although actually gate source won't be that high, will it? But no, it will on this one, because the on voltage here is relative to source at 0 volts. So yeah, these MOSFETs may have a wider spec on the maximum gate voltage. It's a very interesting circuit. Now the MOSFET driver here for these higher voltage cells can't be referenced to 0 volts. So it can't actually take its signal from this little oscillator. So it doesn't. It takes it from one of the MOSFET gates up at the top of the lower array. So it's all very asymmetrical. And since this is using essentially two of these active balancers with this overlapping situation, what's to stop me using a 3S, a 4S, and another 3S? That's going to give me 4. Because of one overlap, only 2 of these can be counted, and only 2 of these can be counted. So it's 2 plus 4 plus 2. That will give me an 8S balancer by using a 3, a 4, and a 3. Now, if you're thinking these are very tiny balancers for these fairly large cells, well, given enough time, they bring all these cells into perfect balance because they're not measuring anything. They're just literally transferring charge between all the cells. And so eventually they all end up exactly the same. Well, possibly, although you could argue that since these MOSFET gates are driven in very different ways, they might have different parameters. But that aside, now sodium ion has a very interesting discharge curve. it sort of drops off at the top, comes down, there's a little bump, and then it drops off sharply at the bottom. But there's enough slope on here that at any point on this discharge curve, if you align the cells, you're going to get them all pretty much bang on. And that means that as long as you give this time to balance all the cells, then you could pull quite heavy currents from this, 4 or 5 amps. And as long as you don't go too near the top and too near the bottom, they should all stay in pretty good balance. Now, something else I think is quite important is being able to monitor the cell voltages. So I recently bought this, and I'll show you how it works. Now, you probably saw my chopped up battery testers, the BT168s, on my battery in the shed. Well, this is an alternative to that. This is a cell voltage display. And so what I've done is I've attached the cable that came with it, which is this 5-way cable, to this little 4S sodium ion battery pack that I built, and put a 4S balancer on. So let's connect this up. I think it's like that. And you'll see that this displays the pack voltage and the individual cell voltages. Let's get in a bit closer. That's set to timeout. Now I think if you press this switch number 2 to on, it locks this display on. You can turn it off and turn it on again, but it doesn't time out after 15 seconds, which it does if that's on the off position. The other switch inverts the display, so it's upside down, but I'm going to want that set to off so that it's this way around. So you can see the cell voltages. Now, something rather strange happens immediately after I plug this in. I don't know whether there's perhaps an extra load on cell 1, but for some reason it seems to read the cell 1 voltage a bit higher than the others. So these are, when it all settles down, these are 2.88. Yeah, 2.88. Oh, but this one's 2.885, which is strange because immediately you plug this in, and you probably didn't see it because the camera wasn't in an optimum position. These would all show the same. I mean, I'm quibbling here over a millivolt, or in this case about 4 or 5 millivolts of error. It's pretty tiny. I mean, these are all reading essentially 2.88 volts, so it's good to 10 millivolts. Now, with this very small 4S 18650 sodium ion pack, you can actually watch this drain down. It pulls, I don't know, I thought this pulled about 30 milliamps, which is a fair bit from this small pack. I don't quite know where I got that number from, but that's my thought at the moment. So yeah, you can visibly see the voltage on this going down. Of course, you can turn it off and then it uses a lot less current. This is a product from Heltek BMS, and you can see here it's model LS04SA. And I've just today received something else from Heltek BMS. And it's this thing. It's a model BT04S05B. Now, this is one of these active balancers. This is a 5 amp using, what's the technique called? Transformer feedback energy transfer. So you've got all these windings, which they've handily color coded in different colors, so you can see how many sections there are. A load of MOSFETs in a ring around here, and this rather nice semicircular heatsink glued down onto the MOSFETs. But it's a 4S balancer. Now they do a 10 amp one of these, and I'm thinking that might be good for those LTO cells. The problem is this is NCM and LFP when the switch is up, and when it's down it's NC, not connected. So I don't know whether this actually does LTO, because the 8S versions of this, 8 cells, which I think can be used between 4S and 8S, have LTO marked on the this switch in this bottom position. So I need to do a little bit more research on this. But this came with all sorts of bits, a high current cable, because as I say, this is 5 amps. I suspect these components down here are polyfuses, 5-amp polyfuses. So you get that. But you also get another display. Now this display looks very similar but subtly different. So from the front it looks virtually identical. It's got the switch, it's got the two dip switches, but on the back it's quite different because it's just got a microcontroller and a little bit of circuitry there, whereas this has got a microcontroller. This chip here, which I can't get data on, but it's a Linsi chip, Linsi. That's the name written on it, and it does appear to be measuring the 4 cell voltages. So this one has the cell voltage measurement on it, whereas this is just a serial interface. So I suspect that just goes straight into the microcontroller. Got a feeling the layout of this is different. I might try and power this up today, actually, have a look at it. But that Linsi chip, which I think is doing the cell voltage measurement, is here. It's actually on the active balancer, and it looks like it's measuring 4 cell voltages across there. So let's get this powered up. I'll connect it to that 4S sodium ion with the big green cells and see if we can get this display fired up. Okay, the sodium ion 4S is connected into here. The display is hooked up to this serial data cable. This just has 3.3 volts, ground, RX and TX. So let's switch it on like so. This comes on. We've got some voltages, and that green run light is flashing, and the voltages are, let's get closer. Oh, and I think the switches do the same thing on here. I think that one probably is the 15-second disconnect. So the voltages all look pretty good there. 14.8 volts. Yeah, that's what I charged it to yesterday. So that's bang on. 3.699, 701, 701 and 700. Now that's well, that's using both balancers now, of course. The little 4S active balancer on top of the sodium ion pack, but also now this balancer. I can't imagine that's going to be warm because these cell voltages are all the same, so it's really not having to do any work. Let's just check that switch 2 does the display invert. Yes, it does the same as the other one. So functionally they're the same, but the interface here, this is a serial data interface, whereas this is a 5-wire actual cell measuring interface. But yes, essentially they do the same job, and that's, yeah, very precise. Now I was just wondering what this switch on here does. If I press it and hold it, the run light stops flashing, and then this goes to all zeros. So it's obviously some sort of microprocessor reboot switch, microcontroller reset switch, and the serial data transmission stops. Let go of that switch, this starts flashing again, and the serial data carries on. So yeah, it'll be interesting to test this 4S high current 5-amp active balancer, but I want to really use this on my LTO cells, because my LTO cells blew up one of those very tiny active balancers. But this doesn't have the LTO setting unless you get the 8S unit, and then that doesn't let you run it at 3S. I've got a feeling this works for 3S or 4S, I can't remember. But I'll put links to all these Heltek BMS things in the description below this video. Now I just wanted to say one thing about price. This is around $10–11, I think. Of course it's more when you add VAT and shipping. I think it's about 14. But relative to chopping up 4 of those little BT168 battery testers, the price isn't massively different, because I think they were about $2 or $3 each, and this is a lot more convenient. I would need 2 of these, of course, for an 8S pack, but yeah, a lot more convenient and a lot less time consuming than all the modifications I was doing to those battery testers. Now what if I put a car headlamp bulb, this 55-watt car headlamp bulb, across one cell of the sodium ion pack? This is going to be a bit tricky, my arm's going to come into shot here, and see how quickly this unbalances. Is that on? Yes, that's on. How quickly is this unbalancing? 6.73 on cell 1 and 3.673. But what if I turn... now can I turn this off? Actually, I probably can turn it off if I press and hold this reset button. Oh, but then I don't get to see the data, do I? 3.672. And if I turn this balancer off, it turns the display off. So I can't really see what the effect of that thing is. Actually, if I turn it off for a while, let's turn it off for 5, 6, 7, 8, 9, 10 seconds, that sort of length of time. See how far out of balance it's gone. 3.669. Okay, let's take off the bulb because that's stressing that cell. Not unreasonably, but how quickly does this go back into balance? So we've got 3.699 on the upper 3 cells. Is that running? Yeah, that is running. Now, is this warm? Can't feel any warmth on it. But yeah, cell 1 is creeping back up. 3.691, 3.692. So that is going to push that back into balance. I've disconnected the little 4S active balancer on top of the sodium ion pack. So that does seem to be working. It'd be nice to be able to see currents and things in these cables, but that will have to be for another day. Okay, I'll leave it there. That's where I am at the moment, looking at sodium ion, looking to take this one to 8S, mainly because of those light strips that I bought recently and made a video of. I'll put a link in the description below, which can take anything up to 85 volts. So sodium ion, 32 at the top, 16 at the bottom, will be ideal for those light strips. But yes, I'm thinking about balancers, and I'm also thinking about balancers without BMSs. But that's it for this video. Cheerio.